Hello friends, I am Dr. Sharmishta Lahire. I am teaching physics in Sri Aurobindo College for the past 28 years, and today I will be talking about the lattice vibrations. About lattice vibrations. In my last lecture, I had talked about the lattice vibrations in a homogeneous isotropic line. In today's lecture, I will be talking about the one-dimensional lattice vibrations in the vibrations in a one-dimensional line of atoms. Let us consider a vibrational motion of a non-homogeneous medium. And in this case, the medium is a one-dimensional chain of identical atoms of mass m, which are connected by ideal Hooke's law spring. Let me consider mass of atoms which are spaced equally, spaced at a distance a from each other. Let A first be my nth atom. On the right of it will be my n plus 1th atom, n plus 2th atom, and so on and so forth. On the left will be my n minus 1th atom, n minus 2th atom, and so on and so forth. At equilibrium, the atoms will be situated equally spaced and their sites will be represented by n minus 2, n minus 1, n, n plus 1, n plus 2. The x coordinates will be n minus 2a, n minus 1a, n a, n plus 1a, n plus 2a. A is the interatomic spacing at equilibrium. When the vibrational motion is excited, then they will execute a periodic motion about their equilibrium position. So, let the displacement of the nth atom from the equilibrium position be un. As you can see in the figure, let the displacement of the nth atom, let it be un. The displacement of the n plus 1th atom, let it be un plus 1. And the displacement of n minus 1th atom, let it be un minus 1. Then let's assume that the forces, we will assume in this case, the forces between the neighboring atoms are linear forces. That is, the force that is required to produce the displacement is proportional to the displacement. I am considering that these atoms are connected by, assuming they are connected by ideal Hooke's law spring. So, the forces between them will be linear forces, that is, the force required to produce a displacement is proportional to the displacement. And second assumption is only significant forces between the atoms are due to the direct nearest neighbor interactions. That means, on the nth atom, the force will be exerted only by n plus 1th atom and n minus 1th atom. So, the force in this case, if beta is the spring constant of the springs, then the force in this case will be given by beta into un plus 1 minus un minus beta into un minus 1. If we simplify, this will reduce to beta un plus 1 plus un minus 1 minus 2 un. Let this be my equation number 1. The influence of the atoms other than the nearest atom, say n plus 2th atom, on the nth atom will be only via the n plus 1th atom. Similarly, n minus 2th atom will exert a force on the nth atom via n minus 1th atom. But those influences will be negligible and we will consider only the nearest neighbor interaction. If we apply Newton's second law of motion, then m d square un, the force on the nth atom, m d square un by dt square will be beta un plus 1 plus un minus 1 minus 2 un. Let this be my equation number 2. Here d square un by dt square is the acceleration of the nth atom. The periodic solution of this equation, equation number 2, will be, this equation will be a running wave equation, un will be u naught e to the power of I omega t minus k n a. Similarly, I can write the running wave solution for the n plus 1th atom and the n minus 1th atom. And for the n plus 1th atom, the solution un plus 1 will be u naught e to the power of I omega t minus k n plus 1 a, and un minus 1 will be u naught e to the power of I omega t minus k n minus 1 a. I have marked these as my equation number 2 and equation number 3 and 4. To find a solution for equation number 2, we have to simply substitute these two equations 3 and 4 back in equation number 2 and find a solution. So, if we substitute the equation number 3 and 4 back in equation number 2, then we find that this will equation number 2 will reduce to minus of m omega square will be equal to beta e to the power of I k a minus 2 plus e to the power of I k a, or this whole square or e to the power of I k a, sorry, and this way I can write it as beta e to the power of I k a minus 2 plus e to the power of I k a. I can write it as e to the power of I k a by 2 minus e to the power of minus I k a by 2 whole square. So, this equation reduces to minus of m omega square becomes beta e to the power of I k a by 2 minus e to the power of minus I k a by 2 whole square. Now, we know that sin x can be written as e to the power of I x minus e to the power of minus I x by 2i. So, sin square x will be minus of 1 by 4 e to the power of I x minus e to the power of minus I x whole square. So, this my equation reduces to minus of m omega square becomes equal to minus of 4 beta sin square k a by 2, or omega becomes equal to plus minus under root of 4 beta by m sin of k a by 2. This becomes my equation number 5. In this case, I can also write it as omega becomes equal to plus minus 2 by a under root of c by rho into sin k a by 2. Also, I can write it as plus minus 2a 2 by a vs sin k a by 2, because we know that rho equal to m by a, rho is the density and beta is c by a. Now, the point is, in this equation number 5, omega has a plus and a minus term, but frequency can never be negative. So, in this case, we have to neglect the negative term, and sin theta also can be both positive and negative, but we have to, because frequency can never be negative. So, omega can have values of only under root of 4 beta by m, only the positive term, and mod of sin k a by 2, or this can be written as 2 by a vs mod of sin k a by 2. So, the solutions of equation, these are the solutions of this equation number 7 are the solutions of the form provided by the periodic function. This equation number 7 now is the dispersion relation for the monatomic chain of atoms. If I plot the dispersion relation, that is the variation of omega versus k only in the first Brillouin zone, which extends from minus pi by a to plus pi by a, then it will be represented by the solid line. The dashed line represents the omega, the dispersion relation for the homogeneous line of atoms, for the homogeneous isotropic line. The solid line now represents the dispersion relation for the monatomic chain of atoms. Now, let us study the effect of this dispersion relation in the low frequency range, high frequency range, and at a frequency of under root of 4 beta by m. In the low frequency range, when k tends to 0, that is the long wavelength range, then in this case sine of Ka by 2 will tend to Ka by 2, because we know that when theta is small, sine of theta tends to theta. Okay. So, my omega becomes equal to 2 by a Vs Ka by 2, and this reduces to Vs into K. Omega becomes equal to Vs into K. This is same as that of the homogeneous continuous line. This shows that in this case again the phase velocity is given by Vp equal to omega by k. Vp is omega by k, and the group velocity Vg is d omega by dk. So, both of them are constants and equal to Vs. In this case again the phase velocity and the group velocity are equal and equal to Vs. So, for the long wavelengths, the atomic nature of the chain is of little importance, and as far as the dynamical behavior of the system is concerned, it behaves as a same entity. The long wavelength, the waves would not be sensitive to the discreteness of the medium. In this case, the discreteness of the medium will not be an important factor, and it will vibrate as a whole. That is, the large number of atoms in this case will participate as if all the displacements are same as that of a homogeneous line. Now, let us consider the next case at high frequencies. At high frequencies, K tends to infinity, then the phase velocity Vp will be given by omega by k. In this case, will be given by V by S, Vs upon Ka into sine of Ka by 2. The group velocity Vg will be given by d omega by dk, which is Vs cos of Ka by 2. In this range of frequencies, what we find is now Vp and Vg, they are both function of K. K means 2 pi by lambda, and this means they are related to they are not same, and in this case the velocities, they are a function of frequencies. So, when light passes through a medium, the refractive index is a function of frequency, dispersion will occur. So, when light passes through a medium where the refractive index is a function of frequency, then it will be act as a dispersive medium, and there will be a dispersion. That means different frequencies will propagate at different velocities. So, for high frequencies, this becomes a dispersive medium. The monoatomic chain of atoms, it behaves as a dispersive medium. For the low wavelength at high frequencies, the dispersive effect is negligible, while when we come to a high frequencies, it becomes dispersive. Now, let us consider the case when omega becomes equal to under root of 4 beta by m. This is the maximum possible frequencies. If we go back to our equation number 7, we will find that sine of Ka by omega will become equal to, if we go back to my equation number 7, then omega can become equal to under root of 4 beta by m only when mod of sine Ka by 2 becomes equal to 1. Okay. This means my Ka by 2 can have values only equal to n pi by 2, or K can have values of n pi by a. If n equal to 1, then K will be equal to pi by a, and K is 2 pi by lambda. This means that lambda equal to 2 pi by a. So, from this equation, from equation number 9, this Vp equal to 2 Vs by Ka sine of Ka by 2, and Vg equal to Vs into cos Ka by 2, we find that Vg will be equal to 0 and Vp will have a finite value. So, Vg represents the transfer of signal and its energy. This means that at frequency under root of 4 beta by m, no signal or no energy will be propagated through the lattice. That means the wave formed will be a standing wave. This is equivalent to the Bragg reflection of the X-rays from the successive planes of the crystal, and the Bragg condition of 2D sin theta equal to n lambda is satisfied. In this case, n is equal to 1, theta is lambda, and theta is 90, and lambda will be equal to 2D. So, only those frequencies which are less than equal to under root of 4 beta by m or 2 Vs by A will propagate down the linear lattice. This means that the lattice is now basically acting as a low pass filter, which transmits only those frequencies which are in the range of 0 to 2 Vs by A. If I consider any other frequency, now let us consider the case that I consider any frequency omega naught. My earlier figure I have shown only for the first Brillouin zone, that is, it is a k value extending from minus pi by a to plus pi by a. If I consider for any values of omega naught and I consider the any values of k, what will happen? K can have any values extending from, I have plotted from minus pi by a to plus pi by a, to the other side 2 pi by a, 3 pi by a, 4 pi by a, and so on and so forth. It can have any. Similarly, on the left the all possible values of k. Now, let us consider any frequency omega naught. Then what we find is that in this case, for any value of omega naught, there will be a range of possible values of k which will give the allowed solution. We see that associated there will be many possible values of k for each value of omega naught. That means that the lattice can propagate several wavelengths at the same frequency omega naught. Several wavelengths can be propagated through the lattice at a same value of omega naught. What does physically this means? Physically this means that the pattern of atomic displacement associated with a certain value of k, say k1, in the range of minus pi by a to plus pi by a at a frequency omega naught can also be associated with several values of k, which means it will be different values of lambda. This is what is shown in this figure. We are showing it for the several Brillouin zone. The first one is extending from minus pi by a to plus pi by a, second extends from 2 pi by a to plus 2 pi by a, and so on and so forth. So, in the central region, that is from minus pi by a to plus pi by a, I have marked it as 1 to 1 and 1 prime. There are two values of k, plus and minus k1. If I look at the figure, there will be two values of k, plus k1 and minus k1, which will satisfy the solution omega naught. I am considering one particular frequency, say omega naught. In the first Brillouin zone region, that is minus pi by a to plus pi by a, two values of k1 are allowed solutions. The positive sign indicates a wave which is travelling along the positive x direction, that is travelling in to the right. The negative sign indicates a wave k1 which is travelling to the left. Then if I go to the second region, there will be, if I go to the second region which I have marked 2 and 2 prime, we find that there are two other possible solutions, k2 plus k2 and minus k2. Then let us look at this region 2 and let us look at the region 2 prime. If I look at this region 2, we find that if we translate this region 2 to the left by an amount 2 pi by a, it will come to the central region 1, and if the second region is again translated by a region, by a value minus of 2 pi by a, it will again come to first one to the left by an amount 2 pi by a, then it will come to region 1 prime. This region marked 2, if it is translated by 2 pi, then it will come to region 1 prime, and on the left it will come to region 1. That means that any arrangement of the periodic, similarly for 3 and 3 prime, again the region can be translated to the region minus pi by a to plus pi by a by suitable lattice translation vector. That means any arrangement of atomic positions representing a sinusoidal wave of any wavelength can be represented or reduced to correspond to a sinusoidal wave which lies in the central region. Now, this region minus pi by a to plus pi by a k value is called the first Brillouin zone. That means I do not have to study for the entire k values, rather if a given value of k it lies outside the first Brillouin zone, then it can be reduced to lie inside the first Brillouin zone by subtracting it by an integral multiple of 2 pi by a. Then the reduced value of k will be represented by an identical value. That means for the lattice, the all values of k need not be studied, rather only for the region k values, if we study for the region minus pi by a to plus pi by a is studied, then the entire crystal will be studied. Again, let me come back to the normal modes of vibration. In this case, again there will be, last one I had considered only the two edges are fixed. In this case, let me consider the case that the first case I can consider it like the I have my monoatomic chain of lattice of length L, the first atom and the last atom. There are number of possible modes, then the number of possible modes of vibration which are independent solutions of equation 2 will constitute the normal modes of vibration, and that will be, there are in this case two possibilities. The first one is the figure A. Let me consider that in this case I consider the length L, nth atom, 0th atom and the last atom, let them be tightly fixed. This represents the normal mode if it satisfies the boundary condition that the displacement of the two ends must be 0. This is the for figure A, the displacement of the 0th atom and the last one, that is the capital Nth atom, let the displacement of both of them be 0. This is represented by figure A. Then the two atoms, they will be fixed. Then in this case again a standing wave would be set up in the lattice. Un is U0 sine of Ka into sine of omega t. Now U0 and sine of omega t cannot be 0. So this quantity Un can be 0 only when sine of Ka equal to 0. This means K will be equal to Ka will be equal to n pi, and this means that K will have values pi upon Na or 2 pi by Na, 3 pi by Na and so on and so forth up to n pi by Na. This means, or k will have values because Na is the length of the chain I am considering. So, Na will be equal to L. So, k will have values pi by L, 2 pi by L, 3 pi by L and so on and so forth up to n pi by L. In order for this equation number 12, un equal to u naught sine of k Na into sine of omega t to represent a normal mode of vibration, k can have values of pi by L, 2 pi by L, 3 pi by L and so on up to n pi by L. Again, k equal to 0 must be excluded since it represents all the atoms that are at rest, which is possible only at 0 Kelvin. So, this value is excluded, k equal to 0 is excluded. Now, k equal to capital N pi by L is also to be excluded because that again represents all the atoms at rest. So, all the allowed values of k are n pi by L, are pi by L, 2 pi by L, 3 pi by L and so on and so forth up to capital N minus 1 pi by L. So, there are n minus 1 allowed independent values of k that are the possible solutions. So, one value of k corresponds to one normal mode. This means that there are n minus 1 normal modes. These are the number of atoms that are allowed to move. So, there are one normal mode of vibration corresponding to every atom which is mobile. There are n minus 1 normal modes. That means there are one normal mode corresponding to every atom that is mobile. Now, let us consider the second case. The second case is represented by my figure B. This will be, in this case, what happens is, let us consider that the two ends of the lattice are free. The two ends of the lattice are free and they have the exactly same displacement when a vibrational motion is excited. This will happen when we consider the lattice of length L inside an infinitely long lattice. That means I am considering only a finite length L inside the lattice, and in this case both the first atom and the last atom, they are free to move and they have the same displacement. Then a running wave will be set up in the lattice. Un will be u naught e to the power of I omega t minus k Na. Boundary condition is the 0th atom and the nth atom is the same. That means u0 will be equal to un plus n. La, length I am considering is equal to Na. So, in general un, I can say displacement of the nth atom will be same as that of the n plus capital Nth atom. So, un will be equal to un plus capital N. These conditions, they were proposed by Born and von Karman. So, these are called the cyclic or the periodic boundary condition. These are called the cyclic or the periodic boundary conditions. So, if I apply equation number 17 in equation number 15, we will find that e to the power of minus I k Na will be equal to 1, which means k can have value 0 plus minus pi by Na plus minus 2 pi by Na and so on and so forth up to capital N pi by Na, or k will have values 0 plus minus pi by L and so on. That means k can have values. This is when I restrict it to the first Brillouin zone. K equal to minus n pi by L will be same as k equal to n pi by L. So, these will not be independent solutions. So, there are capital N number of independent solutions and they are the same number of atoms which are allowed to move. The number of vibrational modes is equal to number of modes that are mobile. Again the spectrum is discrete, the most important point, the spectrum will be discrete and one frequency corresponding to each value of k. This is all for today. And if we consider the density of states, that is the number of modes per unit length, that is defined as k, then that is defined as dk, or dk will be L by pi for the fixed boundary condition and dk will be L by 2 pi for the periodic boundary condition. This and k ranges from 0 to a in the fixed boundary condition, 0 to pi by a, and k will range from minus pi by a to plus pi by a in the periodic boundary condition. That is all for today. Thank you.